Hi, I'm Ruchika, a graduate student in biomedical engineering at Case Western Reserve University. I completed my master's in electrical engineering, specializing in machine learning from IIT Guwahati. I'm collaborating with Neeraj through this machine learning YouTube channel to create a learning resource for the ones interested in machine learning. I will be creating Python and occasional MATLAB implementations of the algorithms discussed in the theory part. Today, I'll explain you how to install Python and write code in Jupyter Notebook. The topics which we are going to discuss today are how to start coding in Python, how to generate noisy sine wave, and polynomial curve fitting. Before diving into the coding part, I would like to illustrate how to install Python. Python installation can be done using Anaconda on Linux, Windows, and Mac. I prefer Anaconda because it is very easy to install and user-friendly. There are two Python versions available here, 3.7 and 2.7. You can download this 3.7 version and install in your computer. It comes with all the popular libraries used in data science such as scikit-learn, NumPy, Pandas, SciPy, etc. In case you need additional packages, you can just install it by using Anaconda prompt. So you can type conda install the package name, let's suppose NumPy, and hit enter. You can see it's already there in the environment. You can also check some other packages such as conda install, SciPy. If it's not there, Anaconda prompt will install it in your Spider or in Jupyter Notebook, and you can start using that packages. And you have to hit yes because you want to install it. It'll take some time and you'll be able to see. Yeah, that's it. Now we are ready to use SciPy in our codes. Anaconda also provides you IPython and Jupyter Notebook. Jupyter Notebook displays into the web browser where you can write your codes and add comments. There are two easy ways to open Jupyter Notebook. One, you can either open Jupyter Notebook using your start menu. This one, you can click it and then you can see it has opened into the browser. So here is your Jupyter Notebook. And now we can open a new file. In case you are not able to locate Jupyter Notebook in the start menu, you can open it using Anaconda prompt and you can write down Jupyter Notebook here. And you will see that it's ready to use. You just need to create a new file and you can start working here. Our today's topic is polynomial curve fitting, but we need to have input and output data points to fit a polynomial equation. For example, here x represent the input data points and you can represent y or z as an output variable where we will create sine wave and use its data points to fit a polynomial equation. Suppose we want to create a sine wave of 100 sample points, so we'll define first n points variable which should be 100. And we'll press shift and enter to execute this command. We can see endpoint should have a value of 100. Now we need to store our x as a NumPy array. So first we load NumPy library using import NumPy as NP. Here import is a function to call NumPy library and we want to call NumPy as NP. Now wherever we want to use NumPy, we can use it as NP. Now we will use x is equal to np.linspace 0 linspace will divide 0 to 1 into 100 equally spaced points. We can also vary the range from 0 to 1 to 1 to 2. or anything else, whatever you need to. Now we can see what are the values stored in X. So we can see here all values lie between 0 to 1 and they are equally spaced. For example, 0 to 0.01 and so on. Now we can create sine wave using X data points. So we can use Z is equal to sine 2 pi X. But in Python, we need to use numpy before sine and pi as they are defined functions in numpy library. Now we need to plot these data points. We will use matplot library for plotting. We'll use import matplotlib plot plt to get interactive plots. You can also specify the size of figure using plt.figure, and you need to use fig size. plt.plot is used to specify variables you want to plot in horizontal axis and vertical axis. Here X is a variable in the horizontal axis and Z is the vertical axis. G represent the color of the plot, so we can see here the plot is green. We can also change it to red, and you can see the plot should be of red color with this. And hyphen is used to represent the marker you use to plot the sine wave. You can also tweak marker size and have multiple plots on the same figure, which we'll see in a short while. Now we have plotted sine wave. We'll add Gaussian noise in the sine wave. So to create Gaussian noise, you can use this command np.random.normal, which will have normal distribution of 0, mean and 1 standard deviation, and points will represent number of points you want to generate. You can see what are the values which are stored in eta. After generating eta, which is a Gaussian noise of mean, 0 and standard deviation, we would like to see how does it look like. So here is a distribution of noise where x represents the same equidistant 100 points between 0 and 1, and we wanted to create a noise across each sample point, and this noise we are going to add into the sine wave to make a noisy sine wave. We stored our sine wave output or vertical axis values into the z variable, which represents sine wave corresponding to all x data points, and we have noise stored in eta. Now add Gaussian noise of 0, mean and standard deviation 1 into the sine wave, and I'm saving the noisy sine wave in, like, I'm showing original sine wave in green and noisy signal into the blue scatter plot, and these are the 100 sampled points after noise which deviated from the sine wave. Now we want to sample 10 points from the noisy sine wave, and we'll use those 10 points to fit a polynomial curve. So let's suppose here I'm specifying that we want to sample 10 points. I'm going to do the same thing as we have done before. I'm using linspace to have 10 points which should be equally spaced between 0 and 1. This represents the Gaussian noise of mean 0 and standard deviation 1. T is the variable which will represent noisy sine wave data points, where I'm adding this Gaussian noise into the sine wave, and I'll show how does it look like. So this was our original sine wave, but we want only 10 points from the noisy sine wave. So here I'm showing a sine wave of 100 data points, but we first use only 10 points to fit a polynomial curve. So I have generated these random 10 points sampled from the noisy sine wave. Now we will fit a polynomial curve within these blue points. So m will represent the order. Here is the polynomial equation, and we'll vary m, that is the order of the polynomial equation, to fit a curve between blue data points which I've shown you earlier. Here m is the order of the polynomial, and polyfit is used to fit a polynomial using x and t sample points, where x is the input and t is the output. After executing this command, we'll be able to identify the coefficients which were obtained after fitting the polynomial curve of third order. We can look at this z variable, and these are the 4 coefficients which we obtained after fitting a polynomial curve of third order. Now we can plug in those coefficients into the third order polynomial using the function poly1d, and we have a function p which we'll use to generate predicted outcome by passing the input data points. So here we can see that we are passing x data points into the function p to get the predicted outcome which we are storing in y. Now we are plotting ground truth sample points using x and t in terms of blue scatter plots and the predicted outcomes in terms of red curve to see how our model fits. When we executed, these blue points are the 10 data points where we wanted to fit a curve, and this red is giving us the predicted outcome, and we are able to see how our model fits over these 10 data points. We can change the order to 4 and see how it fits. Similarly, we can change it to 9 and see this 9th order polynomial curve pass through all the data points. In this way, we can tweak our m, that is the order of polynomial, to see how our curve fits well over training data, and we can fix the m after visualizing the best model that fits most of the data points. However, we also want our model to generalize and predict output of new data points as close to their ground truth values. Hence, we should avoid overfitting and choose a model which works for all data points, including new sample points. So here we'll generate some new sample points. Let's suppose we are generating 5 new sample points using the same way. Here we specified n is equal to 5 to generate 5 new data points, and we'll add noise in the sine wave signal to these new data points to generate ground truth values, which is represented as y new here. Then we need to generate predicted y new to see if our model can identify predicted outcome of new data points as good as it did for training sample points x and t. X and t are the variables which we use to fit the model. Here are the examples of 3 models which we trained using polynomial curve fitting with order m is equal to 3, 5 and 9. We can see all figures have same blue scattered samples called training data, and we fitted models using red curve with different orders of polynomial. Visually, m is equal to 9 seems best to us as our model perfectly fitted over the 10 training data samples. Additionally, mean square error of the model trained with m is equal to 9 is the least as compared to other models' mean square error. However, when we check the model's performance with new data samples shown in green, all behave differently, and the testing mean square error of the model trained using m is equal to 9 is the highest. Hence, this model is not generalized well and overfitted on the training data. In this case, our best model is of order m is equal to 3 because its testing mean square error is minimum. In practical problems, we can cross-validate our model to check the model's performance on validation set by keeping some part of the training data separate to validate, and if our model does well on training and validation data, then it is supposed to do well on the testing data. Our next topics would be basics of probability and rich regression using Python. If you like this video, please do subscribe our channel and stay tuned for our next coming videos.